All right. So thanks everybody for for joining this NLP breakfast, this third edition. Last time we have Peter Martini presenting the rise of language models, and the first time Edward Millman on the right presented some paper on the neural transformer. And today we are going to talk about this paper, an embarrassingly simple approach for transfer learning from pre-trained language models. This paper was published 1 month ago and is bringing interesting ideas in terms of quality and performance for this topic. So what are we going to talk about today? First, what problem are we solving? A little bit of the context. As usual, the architecture overview. It's a close relative to ULMFit, so we'll compare these two architectures and some results and conclusion. So what problem are we trying to solve? Text classification today. And a good way to see where we can apply the paper is to look at the different tasks that the paper claims to be good at. And we have sentiment, emotion, sarcasm, and irony detection. And that the last two, they raise a green flag for us because sarcasm detection and irony detection are hard tasks, and it requires at least a minimal natural language understanding to solve these tasks. So this is a promising paper. A bit of the context. So this paper is built on the rise of two trends: language models and transfer learning. These are not new in the NLP domain, but they got a lot of traction recently. So very quickly, language model, you use it every day when you text or when you use Google. You want to predict the next word when you have the beginning of a sentence. And transfer learning, to solve a task, you will find the easier and similar task that your model will solve first, and you will reuse the knowledge to solve your main task. In that case, we want to solve a text classification problem, and we will first build a language model and continue the training on the specific task like irony detection. So I mentioned earlier that it's a close relative to ULMFit. So ULMFit was the first of this kind. And I think it's better to remind a bit how this works before we jump to the next slide, which will be the architecture of the current paper. So we are doing transfer learning, which means we have two tasks. A first task on the left, language model, and the second task on the right, the classifier for text classification. So on the left, the first task, language model, the input is a sentence, the goal $, and the output here on the top that goes back on the bottom, or we want to predict the next word. So in this paper, we will do the language model on a huge data set to learn the English language distribution. And this knowledge is stored in the layers of the model. These are BLSTM. These are BLSTM layers and a softmax on the top. And when you finally want to detect irony, you will reuse these 3 layers of BLSTM plus the embedding layer, but change the top and switch the last layer to a classifier. Like plus would be irony and minus would be not irony. And so this is a great idea, but it didn't work for a while. There was some problem of catastrophic forgetting, which means you learn the first task, but when you start learning the second task, you forget everything of the first one, and it killed the point of using transfer learning. So the great advantage on this paper was to use a couple tricks to prevent from this catastrophic forgetting. So one of them is the sequential unfreezing, where when you train the last task, you will not train all the model at the same time, but you will gradually unfreeze the different layers. There was also a trick using a special shape for the learning rate. So for each epoch, you would start with a low learning rate, high, and then low again. And there was other ones, or also the language fine-tuning. We have 2 tasks, but we have 3 steps. So that's a bit strange. That's because in the middle, you continue the training of the language model, but on your irony dataset. So why would you use 2? Because the irony dataset is very small and it's not good enough to build a language model. So you will take advantage of a huge dataset in the language model. Another question is, why would you use a language model to help for a classifier? It seems like a language model is a harder task than just classifying text. It's not because the task is easier, but because we have kind of infinite data to train a language model. We just need some books of English, and we can train on it. But for the irony dataset, we need some labels for each tweet in this case, so it is mostly small. So let's switch to the current paper. And it claims that it simplifies the task, and it looks like it because we now only have 2 tasks and 2 steps. So similarly, we have a first task on the left that will do the language model, and the classifier on the right that will find irony in the tweets. Architecture is similar. We have an embedding layer, 2 hidden states. These are not BLSTM, but LSTM. So it's again in terms of computation. And finally, the language model loss. It seems strange to see that we want to predict 4 words, and because the language model is supposed to predict only 1. We can have this kind of representation because we are using LSTM and not BLSTM, which means the flow of information here goes in this layer goes from left to right. So with the, we will predict quick, the next word. With the quick, if we go up, we will predict brown, the next word of the quick, etc. until the end, when we have the full sentence, the quick brown fox, and we will predict jumps. So it's not detailed, but I think this linear layer does not allow the information to flow from right to left, because obviously quick is here and quick is here, so the model will just learn to take the next word literally, to find the next word. So that's for the first step, a language model. So it's more simple than the ULMFit. And the second step is different, and we will look at how they do to tackle the catastrophic forgetting. So now you have red spots here. So the same architecture with red spot. Red spot means transferred weight, which means we have the same architecture, but we also have the same weight that we learn from the language model. So in this weight, we have some knowledge of the language distribution, for example. And if we go right from here, we have this first loss, this classification loss. It's very similar to the ULMFit paper. They just add another layer of LSTM here. They are gray, which means the weight will be learned from this task. And what's new is that now we have an auxiliary LM loss. So we are multitasking here. We are learning 2 things at the same time. the classification task, but also here, if you look, it's exact same task as before. So we are basically continuing to learn a language model in the irony dataset. So we could see that as merging the two steps here, the language model fine-tuning and the classifier fine-tuning. So it obviously makes things easier to use.
So are the bottom two layers frozen, or are they just transferred and fine-tuned?
Yep, that's a good question. So they are first transferred as is, but then they are trained.
Okay.
And they are also using the same trick as ULMFit, the gradual unfreezing, which means they will be unfrozen one layer at a time, kind of. That's the main idea. So this is an interesting way to tackle the catastrophic forgetting by learning the two tasks at the same time. And obviously, in the end, you are only interested with the classification. So what they propose is to slowly in time remove this task and focus only on the classification. And they use some exponential decay. So which means at the beginning, this task will be a main task, but the weight of this task will exponentially decay until 0, so that in the end we are only learning the classification.
Over training epochs?
Over training, yes.
Okay.
And yes, and I think the goal is the same, is just for catastrophic forgetting, not to forget the first task, to keep the knowledge of the English, and not overfit the irony transet. So about the results, so on the left, they use ULMFit to compare their architecture, SiATL. And on these 5 data sets that we mentioned before, we can see that the line,
solid and dashed.
The solid line is always on top of the dashed line.
Solid their results, or solid is?
So solid is their results, yes, okay. And dash is the older ULMFit. So that's good. They are improving the ULMFit model.
I have a question. So
yes,
for the comparison, so they say they are comparing compared to ULMFit. What they did exactly on ULMFit on the model for classification? Yep. Because there is say you can gradually adapt or transfer according to this dataset data, and in the second time put a classifier on the top, or they directly put the classifier on the top of ULMFit without changing the weight of the lower layer. What is the comparison?
Yeah, definitely.
Thanks.
So it's a good question, and I would have to introduce that this paper, they pre-trained on a Twitter dataset, a huge corpus of tweets. And ULMFit was released with a pre-trained model on normal English.
Okay.
So what they did here is they pre-trained ULMFit on the big corpus of tweets.
Yeah.
And then they build, they use the same methodology as ULMFit with all the tricks, sequential, gradual unfreezing, to solve these 5 tasks.
Okay.
So the same corpus for the language model training, and then the same methodology for the. So it seems I think it's a fair comparison.
Yeah. Thanks. Okay.
The only point we can discuss later is so all the results are only on a tweet corpus, and the question would be, is that generalized on normal English? So that's the question I asked the author, and I think she will answer this week.
Cool.
So that's the good news. better improving the ULMFit model and also improving it with low data, in low data environment, which was a great improvement provided by the ULMFit. So this paper keeps the same advantages. Computationally speaking, it's lighter. LSTM used instead of BLSTM. That's an example. It's easier to tune because we have one less step. So I wouldn't say that ULMFit was embarrassingly hard to tune. At Feedly, we could use it very quickly on any Kaggle dataset or internally. But this is definitely easier to use and tune. One less step. And we don't have the slanted triangular learning rate, which is the adaptation of the learning rate over time. That was used at ULMFit. So on the results published on the paper, so the current architecture is here, SiATL, and they do some ablation study. And what we can see from this is that the auxiliary loss, AUX, is always bringing a lot of value. And as you don't remember, anyway. You have the result of ULMFit, and as I said before, you could train ULMFit on Twitter corpus or on Wiki, on our main English corpus.
SU is sequential unfreezing.
Thank you. Thank you. I was thinking it was gradual unfreezing. Thank you, Eric. And as this architecture beats ULMFit, most of the time it's not the state of the art. Here they mentioned the state of the art for each task. I look a bit at these papers, and they are mostly result of the competition where this dataset were released, and they could use some very complex architecture. For example, the second one was using an ensemble of 10 CNN and 10 BLSTM architecture with sub-voting, so it doesn't mean that the paper is worthless. For us, we would prefer use the simple architecture than this one. And for the last one, they use some extra data, a very smart way to gain knowledge with using 1 billion words of tweets and the emojis in the tweets. So in conclusion, when would we use this paper? I think it's a good fit for text classification, good fit if the class classification requires some understanding of the English. I'd say it's mostly on short document, but it's for Feedly. In Feedly perspective, we are mostly using news articles, and this architecture is working well on short documents like tweets. It's more computationally effective. That's good. And the question is, how does it perform beyond Twitter-like text? Does it perform well on news for us, for example, or any other general English application? And the code release, they mentioned they will release it and in the next upgrade of the paper. So this is not there yet, and hopefully it will. Right, thanks everybody, and for listening.
Thank you, Stéphane.
Thank you.
Yeah, thanks a
Thank you
lot.
for hosting.
Thanks.
Very clear. Sorry, I can't join you for the croissant.
Next time.